Hello, in this video I'm going to explain multiplying fractions. So when we multiply fractions, the rule says to multiply straight across. And after you multiply straight across, you have to reduce all the way down to the smallest number in the fraction possible, basically to lowest terms. All right, so let's begin with example number 1. So we have 3/5 times 6/7. Now, one thing I want to mention here, and it's also in the help, that when you're multiplying fractions, this multiplication dot right here, you can think of this multiplication dot between two fractions as a bridge between the fractions. You can think of this as like this, and then the multiplication here. So I'll do this once or twice, but I think you'll understand the concept here. So this is the same as 3/5 times 6/7, and then this multiplication dot becomes this bar here. So in other words, you have this long division bar, and on top, in the numerator, we have 3 times 6, and in the denominator, we have 5 times 7. And the reason I'm mentioning this is because if it's possible, then you can reduce numbers. You can cancel numbers if it's possible. But in this case, we see that we have a 3 here, no 3s here, a 6 here, no 6s there, 5 here, no 5 here, 7 here, no 7. We cannot reduce this. So all we can really do is just multiply straight across. So we have 3 times 6, which is 18, over 5 times 7, which is 35. So if you cannot reduce here, if you cannot cancel this to make it a smaller fraction, then guaranteed your final answer is already fully reduced. So don't even bother checking here to reduce, because it will not. Because if you go backwards from here to here, like we've done in previous videos, we can see we cannot cancel. All right, so before you multiply across blindly, look to see, can you cancel? Can you reduce? And in this case, we could not. So our final answer is 18 over 35. So the rule says when you're multiplying fractions, multiply straight across. And if you need to, reduce the answer. All right, so let's put in there 18 over 35. All right, so let's try number 2. One third times 3/8. And recall that 1/3 times 3/8 could be written this way, right? Like I just mentioned. These are equivalent ways to represent multiplication of two fractions. Now, look, can we reduce? Before we multiply across, let's see, can we reduce? We have a 1 here, which doesn't really reduce, right? 1 doesn't get any smaller, so don't even bother trying to reduce 1. But here we got a 3, and here we got a 3. So yeah, they reduce, they cancel out. What really happens here, and I touched on this a little bit in the last video, is that we're thinking of a number that divides into 3 and 3. What is that number that divides into 3? 3, of course, itself. 3 divides into 3 one time, so put a 1 here. 3 divides into 3 one time. Now, we don't bother doing this if it's the same number, right? We just slash it out. And you should put a 1 there as a reminder that there's really a 1 there. It's not, it doesn't just go away. It's just 1. And 1 times that other number is the other number. 1 times the other number is the other number. So you really technically should put a 1 there as a reminder that 1 is there. See, now we reduce this, now multiply across. So what do we have? 1 times 1 is 1. 1 times 8 is 8. So 1/8 is the fully reduced answer. Now, the reason I bring this up here about putting like a bridge across two fractions, it's not necessary to do that. You really could do it right here. And that's what I would recommend going forward. You could just do it right here. 1/3 times 3/8. You can avoid this intermediate step by knowing that this multiplication creates a bridge for these two fractions. This is the same as this. So now what you can do is say, okay, let me see if I can reduce before I multiply. And the way you do that is you look up and down to reduce. Is there a number here that's the same as here? No. And then you look up and down over here. Is this number the same as this number? No. Which is similar to doing this. Looking to see if 1 is the same as 3 or 3 is the same as 8. No, so they're not. Now, notice here that we went on a diagonal. So what you also have to do is look diagonally to reduce. So then you look this way and you say to yourself, what number divides into 3? And that number is 3. 3 divides into 3 one time, slash the 3 out, put a 1 above it. 3 divides into this 3 also one time, slash the 3 out. You got to do that, or else you might multiply with a 3. Slash the 3 out and put a 1 there. Okay, so we can cross this out. We don't need it anymore, right? Cross that out, don't need it anymore. Now we should also look diagonally this way. Now, whenever you have a 1 involved and you're trying to reduce, you cannot reduce because 1 is as low as it goes. The only number that divides into 1 and 8 is 1, but that doesn't help any. 1 divides into 1 one time. 1 divides into 8 times. We're back where we started. So when you have a 1 involved, don't try to reduce a 1. All right, so now that we did this here, you multiply across. 1 times 1 is 1. 1 times 8 is 8. So see, we circumvented this middle step here. We went from here to here. Just be careful, though, when you do the slashes and you add the numbers here. Try to stay neat, because if you get a little sloppy, you might multiply the wrong number. And always put a X through here, to get rid of this thought bubble when you're done, right? This is that thought bubble I talked about in the last module. You don't want to leave this 3 hanging out like I did there, because you might accidentally multiply by that. No, we don't multiply with this thing, okay? So 1/8 is our answer. Let's try it and see if it works. All right. So let's try the way that I explained it to you. 2/7 times 1/10. Are we going to multiply across and reduce at the end? No, we're not going to do that, because then we have to reduce a huge number. You don't want to multiply first, then reduce, because then you have to reduce a big number, and it's much more difficult to reduce a big number, look, than smaller numbers. These are smaller numbers. They already broken down for you. So it's easier to reduce right here. So let's look over here, up and down. Is there a number that divides into 2 and 7 besides 1? No. Well, we have a 1 involved. Don't even try to reduce. Nope. So let's try diagonally then and see if we can reduce diagonally. By the way, before I forget, you cannot reduce side to side. do not reduce side to side. You cannot do that. Okay? You cannot do that. Just like if it was this. So you cannot reduce side to side, right? You cannot do that. For the same reason you cannot reduce side to side here, you cannot reduce side to side there. Only multiply side to side, okay? Be careful of that. All right, so 1 does not reduce. Let's look diagonally. Well, again, we got a 1 involved. It does not reduce. Well, our last chance is to look diagonally this way. Oh, wait, I see something. What number are you thinking about in your thought bubble that divides both into 2 and 10? And don't say 5, because 5 does not divide into 2. 5 divides into 10, but not into 2. That number that you're thinking about has to divide into both. And that number is 2. 2 divides into this 2 one time. 2 divides into 10. Here's your 5 right here, right? Here's your 5 right there. That's where the 5 belongs, down here. 2 divides into 10 5 times. Cross out the thought bubble. Multiply straight across. 1 times 1 is 1. 7 times 5 is 35. If you fully reduced here all the way, guaranteed your final answer will be fully reduced. Guaranteed. If you did not reduce all the way, then you got to reduce again. Okay, so keep that in mind. If you didn't go all the way down, in this case, there's only one way to reduce, right? But you might have an example where you can reduce incrementally. It's not the end of the world, but always remember, if you don't reduce all the way, then you got to reduce again later. Because your final answer has to be completely reduced to the lowest factors. All right, lowest terms. So here we go. Let's put that in there and see if it works. All right, now we have a strange looking problem here. Okay. Whole number 2 times 3/2, a fraction. Huh, that looks strange. Now, do not confuse this with a mixed number. This expression is not 2 3/2. It is not that. The reason it is not that, the only way you would know is that you see a multiplication dot between the 2 and the 3/2. So we know this is not equal to this mixed number. Do not confuse the two. They're two different things. This one, remember, as a fraction, you multiply here. 2 times 2 is 4, plus 3 is 7. This is the same as 7/2. Different animal altogether. All right, so keep in mind, don't confuse this with that. Now, that that's out of the way, how do we handle this? All right, so let's go back to just the whole number. Let's use the number 5. We have the number 5. Okay, so this is the number 5 right there. What would happen if I put a division bar and a 1 underneath it? What would happen if I have the 5, the original whole number 5, as numerator, and then I divide it by 1 in the denominator, right? The 1's the denominator. So what is the actual answer to this? What's the answer to 5 divided by 1? Well, the answer is 5. So look, this is equivalent to this. Why am I showing you this? Because it's going to help you out here. So remember, you can always put a 1 under any number and it won't change that number, because that number, whatever it is, divided by 1, it gives us that number. So a nice way to rewrite this expression is this way. Change this whole number 2 as 2 over 1. Put your multiplication dot there, and then 3 halves, like that. Because now we know how to handle this, right? We know how to handle this situation. Reduce first, then multiply across. This way, it's kind of hard to know. Am I multiplying 2 times 3 or 2 times 2? What am I doing? You know, it's hard to know. Just remember, this whole number is really the numerator. It's the numerator. This is the numerator. It's not that easy to tell here, right? Like, it's like in the middle. It's in the middle of a fraction. It's hard to tell, what is this thing? Well, this thing is a whole number. But if you rewrite the whole number as a fraction, then it's easier to see what you have to do. So here we go. Is there a number that divides into 1 and 2? Well, we got 1 involved. We cannot reduce. How about 3 and 2? Nah. Let's look diagonally now. So I'm looking up and down to reduce, and now I'm going to look diagonally. Well, over here, we got a 1 involved. We cannot make 1 any smaller. Don't even bother trying to figure it out. But look there, right? Look at that. What number are you thinking about in your thought bubble that divides into 2 and 2? You said 2, correct. 2 that you're thinking about divides into this 2 one time. 2 that you're thinking about divides into this 2 one time. Cross out the thought bubble. We don't need it. It's time to multiply straight across. 1 times 3 is 3. 1 times 1 is 1. And am I going to type? Let's type that in there. So let's see. That's it, right? So I'm going to type in 3 over 1 because I'm pretty sure that's the answer. Oh, no, it's wrong. Why is it wrong? Oh, yeah, that's right. I forgot. We cannot have a 1 in the denominator, or else they're going to mark it wrong. Because, see, this is not fully reduced, right? Because what is 3 divided by 1? 3, you said. 3, you said. Nice. All right, more multiplication fun. So let's see this one. All right. 9/8 times 2/5. We're not going to multiply across. We're going to reduce first, if possible. Does this reduce? No. Does this reduce? No. Does that reduce? No. Does that reduce? Yes. What number are you thinking about that divides into 2 and 8? And tell me it's not 4, because 4 does not divide into 2. All right? The number you're thinking about has to divide into both 2 and 8. And that number is 2. 2 that you're thinking about divides into this 2 one time. 2 that you're thinking about divides into 8 4 times. See, here's your 4 right here. Not in there, right here. Now, cross out the thought bubble and multiply straight across. 9 times 1 is 9. 4 times 5 is 20. And this is reduced all the way because we reduced as far as we could here. Let's try 9 over 20. All right. And here we have more multiplication fun. 9/5 times 7/6. So, can this reduce? No. Cannot reduce? No. Cannot reduce? No. Cannot reduce? Yes. What number are you thinking about that divides into 9 and 3? What is that number? Oops, I gave it away. What number divides into 9 and 6? And you said 3. I gave it away. So this number has to divide into both of these, and then that number is 3. 3 divides into 9 3 times. 3 divides into 6 2 times. So make these big enough so you can see these, right, when you multiply across. Don't make them too small because we have to multiply with these at the end. Cross out the thought bubble, multiply across. 3 times 7, 21. 5 times 2 is 10. And there it is. 21 over 10. Now, I'm going to do, you're not going to see a problem this hard until module 7 of Math 50. So that's pretty far in the future for you. But you know what? It's the same concept. So I'm going to do a pretty difficult one here. I'm going to do a pretty difficult one. I'm going to use some of these. Actually, I don't want to use the same numbers, right? So let me try this. 24 over 10. I know these are huge. Bear with me. This is a little side trail that I'm taking. But watch what I'm doing. And then let's call this 25 over 6. Look at this thing. Do you want to multiply across and then reduce? I don't. I don't want to multiply this out. Whatever 24 times 25 is, that's huge. 600, I think, something or other. So 600 something or other over 60, and you're trying to reduce that, good luck. So this is a good example of where it's really beneficial to reduce before you multiply. Here we go. Can we reduce this? Actually, we can, right? Because they're both even numbers. We could reduce. Yeah, we could reduce. Nothing wrong with doing that. But also what I'm eyeballing, I'm already ahead of the game here. I'm eyeballing this. This reduces really nice. That reduces pretty nice too. So this reduces by 2, but this reduces by more. It doesn't really matter in the end because you can keep reducing, right? You just like stacking cards. You keep reducing, keep reducing. So I want to maximize my reduction right off the bat. There's no right or wrong with reduction as long as you keep reducing. So I'm going to hold off on reducing by 2 And I'll come back to reducing the 24 in a minute. Does this reduce? No. Now, does this reduce? Yeah, sure does. Now, what is the biggest number you can think of that divides into 6 and 24? Is it 2? No, don't say 2. It does go into both. It's not the biggest. Don't say 3. 3 does go into both. It's not the biggest. You said 6. Correct. 6 is the biggest number. You want the biggest number that divides into both to get the maximal reduction. So 6 is the biggest number that divides into 6 and 24. 6 divides into 6 one time. 6 divides into 24 4 times. Cross out the thought bubble. We don't need it anymore. Wow, we made a huge difference in that reduction, right? We're reduced by a factor of 6. Nice. And let's look one last way this way. Can that be reduced? Is there a number that divides into 10 and 25? And knowing your multiplication tables, you said yes. 5 does. The 5 that you're thinking about divides into 10 2 times. The 5 that you're thinking about divides into 25 5 times. Cross out that thought bubble. Now, again, be neat here, right? Be neat. If you get sloppy, it's going to be easy to make a mistake. Now, we could multiply across right now. It won't be the final answer, but we could, just to break the problem down to steps. We could. The reason it's not the final answer is because you got to eyeball this again. And look, you got 2 and 4, right? Yeah. This reduces, the 2 and 4 reduce, the 5 and 1 does not reduce, the 1 and 4 does not reduce, the 2 and 5 does not, the 4 and 2 reduces. So let's do it right here, since we're at it. What number divides into 2 and 4? And you said 2. 2 divides into this 2 one time. 2 divides into 4 2 times. See that? Okay. Cross out the thought bubble. Let's take a quick spin around the block here. We have 1s on the bottom, so we cannot reduce anymore because we cannot reduce side to side anyway. Even if we could, we couldn't. Let's multiply this guy out, see what happens. 2 times 5 is 10. Multiply straight across. 1 times 1 is 1. And 10 divided by 1 is 10. Nice. Now, it took me a while to do this because I had to explain it to you. But if you were good with multiplication and you were just banging this out, you'll be done in less than 30 seconds. Whereas if you multiply across a huge number, you would have to use prime factorization to break down the numerator over the denominator, and then cancel stuff out. Too much work here. Too much work. I think it's easier this way. You just got to be careful with your neatness. All right, so that was a sidetrack there. You're not going to see this level of difficulty until Module 7 of Math 50. Okay, so let's keep rolling. So what do we got? We have 18 over 11. After doing that one, this is going to seem easy, right? 5 over 12. Does this reduce? No. Does this reduce? No. Does that reduce? No. Does that reduce? Yes. You said, what is the biggest number that divides into 12 and 18? Hit pause for a second. See if you can figure it out. Okay, we're back. The biggest number that divides into both is not 2. It's not 3. It's definitely not 4 because 4 does not divide into 18. It is 6. right? It is 6. 6 is the biggest number that divides into 12 and 18. All right, now 6 divides into 12 2 times. 6 divides into 18 3 times. Cross out your thought bubble. Let's take a quick spin around the block. Can anything else reduce? Nope. 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 Time to multiply straight across. 3 times 5 is 15. 11 times 2 is 22. And by the way, even though it is guaranteed that your final answer is fully reduced, just take a quick look here, just in case you missed something, right? Just in case you missed something. You don't want to leave something, if this was 16, for example, you don't want to leave something not reduced because it's going to be wrong. So 15 over 22 does not reduce, so I feel pretty confident that that's going to be the right answer. All right, nice big number. Another good example of why you do not want to multiply straight across and then reduce at the end. You want to do that. You want to reduce in the beginning. Does this reduce? Nope, nothing divides into both. Nah. Yeah, that reduces, sure. Because I know my multiplication tables. Now, granted, 3 times 13 is 39. The 13s are not in the multiplication table. But still, 3 times 12 is 36. Another 3 is 39. It's within range of your brain, right? You can do it. Or you can say 3 plus 9 is 12. And then 12 is divisible by 3 using the divisibility rules. Yes, we're back to those. See how helpful they are? Anyhow, so yes, there is a number that divides into 3 and 39, and that number is 3. 3 that you're thinking about divides into 3 once. 3 that you're thinking about divides into 39 13 times. Okay, 13 times. And if you need to use long division on the side to figure it out, fine. Cross out the thought bubble. And are we ready to multiply across? No, you said. Correct. Because we got to look this way. And look, they're both even numbers. They're both even numbers. So what is the biggest number that divides into 10 and 16? And you said 2. Correct. The 2 that you're thinking about divides into 10 5 times. The 2 that you're thinking about divides into 16 8 times. Cross out the thought bubble. One last spin around the block. Nothing reduces. It's time to multiply straight across. 8 times 1 is 8. 13 times 5 is not an easy one, but we know from multiplication tables that 12 times 5 is 60, right? We got that memorized. So we have one more 5 to add. If 12 5s are 60, 13 5s, one more 5, it has to be 65. You said. Now, we reduced all the way here, which means this should be our final answer. See, now we can be confident this is our final answer and not have to spend time trying to reduce this. Time and energy trying to reduce something that's not reducible. Because here, we can see it cannot be reduced. There it is. All right, so 8 over 65. Now, the next problem here uses parentheses instead of multiplication dot. It's really the same thing, right? Because recall from way, way back, Math 25, multiplication could be written in 3 different ways. The times the multiplication dot or parentheses, multiplying with something else, either a number or another set of parentheses. 3 different ways. We avoid using X because when you get to Math 15, introductory algebra portion of it, X is going to be a variable, so we try to avoid that. But just so you know, you got 3 different ways to represent it. Multiplication. All right, last problem. So we have 12/5 times 7/8. Same rules apply. You can think of these division bars as being connected. So we can still slash side to side and everything. Same thing. So we're going to look up and down to reduce, but we can't here. Look up and down to reduce here. No. Diagonally, can we reduce? There's no number that divides into 5 and 7. So our last hope is this way. What's the biggest number, I should say, that divides into 8 and 12? And don't say 2, because 2 is not the biggest number. Instead, you said 4, which is correct. 4 is the biggest number that divides into 12 and 8. The 4 that you're thinking about divides into 8 2 times. The 4 that you're thinking about divides into 12 3 times. Slash out the thought bubble and take a quick spin and see, is there anything else I can reduce? Nope. Let's multiply across for our final answer. 3 times 7 is 21. 5 times 2 is 10. One last peek. Can that reduce? Nope. Nope, for sure. So 21 over 10 should be our final answer here. All right, so this is how you perform multiplication of fractions. If you like my content, click on the like button, post your comments below, and subscribe to my channel. Thank you for watching.